and welcome. In this video session, we will discuss on the POSIX shared memory. In this diagram, we explain the shared memory. So here on the left hand side, let's consider the process 1 virtual memory, and let's say the virtual memory size is 4 GB, and on the right hand side we have process 2 virtual memory, and the size of the virtual memory is 4 GB. Now we have the physical memory, which is nothing but the RAM. So shared memory is nothing but the portion of the RAM, and this portion of the RAM is mapped onto the different process. So in this case, this portion of the memory of the RAM is mapped onto process 1, and the same memory of the RAM is mapped to the process 2. So now any read or write performed on process 1 virtual memory in this area is in fact written to the shared memory on the physical RAM. In the same way, when process 2 performs any memory operations on this mapped region, then the actual read and write is performed on the physical memory. That is nothing but the shared memory. So in this way, both the process, that is process 1 and process 2, can exchange the data via the shared memory. So shared memory is nothing but the common memory that can be shared among the different process in order to perform the inter-process communication. So now in order to create a shared memory, we have to follow the below steps. So first we have to create the piece of memory on the RAM, that is nothing but the shared memory. And the shared memory, usually when we create, it's of 0 byte. Then after that we need to define the size of the shared memory, that is we have to define the length of the shared memory, and then map this shared memory onto the required process. So here in this case we are mapping this shared memory onto the virtual memory of process 1, and similarly mapping this shared memory on the virtual memory of process 2. Once the shared memory is mapped on the different process, read and write onto the corresponding process virtual memory will lead into IPC between the different process. Now let's see the different programming system calls in order to achieve the shared memory. Now as defined, shared memory allows to share a mapped memory region between unrelated process. So in this case, shared memory is very much suitable even to use between two processes which are not related to each other. And the shared memory, when a shared memory is created, there is an entry in /dev//shm. We will see this when considering the example. Also, the shared memory is considered as the fastest IPC mechanism when compared to other shared memory such as message queues, pipes and FIFO. This is because there is no extra kernel data that is involved. Also in other IPC, if a data needs to be sent from process 1 to process 2, then there is two set of copies that is performed. The first set is from the process user space to the kernel space. Then a similar copy is performed from the kernel space to the target process user space. So here in other IPCs, two set of copies are performed, whereas in the shared memory, the data is written onto the common shared memory, and this shared memory can be read or written from the different process. Thus, the shared memory is the fastest IPC when compared to any other IPCs. Now let's see the different functions involved in creating a shared memory. Uh, As a first step, shm_open is used to create a new shared memory or to open a existing shared memory. This is similar to the open system call that we perform in order to open the regular file. Now SHM open returns a file descriptor that is referring to the shared memory. As we have indicated before that a shared memory that is newly created is of 0 bytes in length. Since the length of the shared memory is 0 bytes, we need to define the length of the shared memory. And then finally, as a step 3, we need to map the shared memory to the different process using the mmap function. So as we can see that any read or write to the process virtual memory will be actually read or written from the shared memory. So here, whenever any process performs read or write operation on the mapped memory of the virtual space of the corresponding process, it actually performs the read write directly on the shared memory. Thus, the other process can directly utilize the shared memory. So the syntax to create a shared memory is shm_open, and we need to pass the name of the shared memory and oflag and mode. This is similar to the open system call of a regular file, and if shm_open is success, it returns a file descriptor. In case shm_open fails, it returns -1. So here oflag can take different arguments such as read only, read write. This is similar to the parameters that we defined for a regular open system call. And if we have to create a new shared memory, then EXCL option is provided. So these parameters can be odd while creating. Now let's see how to set the size of the shared memory. As we have mentioned before, the shared memory when it is newly created, the size is 0. So the user needs to assign the required size to the shared memory, and this is done using if_truncate function. So in order to assign the memory, we need to pass the file descriptor that is obtained by shm_open. The shm_open returns the file descriptor. So this file descriptor that is returned has to be passed as the first parameter, and second parameter will be the required length of the shared memory. The example of if_truncate we will be seeing. Finally, let's see how to map the shared memory on the individual process. So here the syntax to map the shared memory onto the individual process is as follows. We need to include the required header files, and mmap is the function that maps the shared memory onto the process virtual memory, and the first parameter at ADDR is nothing but the required process virtual memory on which it needs to be mapped. Usually this address, if we do not have any specific virtual memory of the process, this is passed as null so that the system can take a appropriate memory of the virtual space. And length is nothing but the length of the created shared memory, and PROT is the protection of memory, and usually we have PROT read for read protection or PROT write for write protection. And In case of a shared memory, the flags we need to use as map underscore shared so that the shared memory can be used by different process, or the data that is written onto the shared memory can be accessed by different process. So in that case, you have to mention flags, the value of flags as map underscore shared. And fd is nothing but the file descriptor that is obtained from shm underscore open. So we will be seeing the example how to use all the three functions, that is shm open, ftruncate and mmap. So the mmap on success, it returns the virtual memory of the process to which the shared memory is mapped. So here when mmap is success, it returns the base address of the virtual memory of the process. So we have created a shared memory, and using mmap we have mapped the shared memory onto the process virtual memory. And if mmap is success, it returns the base address of the virtual map. And if mmap fails, then it returns map failed, that is nothing but -1, which is typecasted to void star, and the corresponding error number is set. And we can also see more information of mmap using man space 2 space mmap on the terminal. Now in the next session we will see the example program how to use the POSIX shared memory. Hello and welcome. In this video session we will demonstrate the usage of shared memory. In the first program, we are going to write the data onto the shared memory, and in the second program, we are going to read the data that is written onto the shared memory. First, let's see the program to write to the shared memory. Here we include the required header files, and we begin the program from main function, and we define the required variables, and shm underscore open is used to open the shared memory that is specified in the first parameter. And if the shared memory already exists, it returns the file descriptor of the shared memory. Or if the shared memory does not exist, by specifying o underscore create, we are going to create the new shared memory in the mode 660. This is nothing but read write mode for user, read write mode for the group, and no permission for others. And if shm underscore open is failed, it returns a -1. And now the second step would be to define the length of the shared memory. So in this program, the command line argument parameter is used as the data. So argv of 1 is used as the data that is being returned to the shared memory. So we get the length of the data that is passed from command line argument, and ftruncate function is used to set the length of the shared memory, and we have to pass the required length and specify the file descriptor onto which the length is set for the shared memory. And as a last step, we have to map the created shared memory to the process virtual memory. This is done by calling the function mmap, and the first parameter is null, and the second parameter is nothing but the length of the shared memory, and the third parameter is the protection bits. That is nothing but we are providing a read and write protection, and following that the argument is map underscore shared. This means we are using the shared memory for map shared purpose. That is nothing but the shared memory data on the shared memory is visible to different all other process, and we have to specify the file descriptor and the offset is 0. And if mmap failed, it returns a map underscore failed, and upon success mmap returns the virtual memory address of the process. And finally we copy the data that is passed from the command line argument to the mapped memory. So ADDR contains the virtual mapped memory location, and any read or write onto this mapped memory, the data is written onto the shared memory. So as we have discussed in this slide, that any read or write to the process virtual memory is written onto the shared memory. So here what we have done is we have first created a shared memory using this SHM open and specified the name of the shared memory, then defined the length of the shared memory using ftruncate. We have defined the length of the shared memory, then mapped the shared memory onto the process using mmap, and using mmap we have mapped the shared memory onto the process virtual memory. Now any operation on the process virtual memory in fact writes the data onto the shared memory. Now let's compile this program. So GCC, the name of the program, and we need to specify -LRT, and the compilation is successful and the object file created is shm_write. Now let's go to the read function before executing the write program. Now let's open the read program. So in this program we include the required header files. So this program is used to open the shared memory, that is, and read the data from the shared memory. So in this case we open the shared memory and specify the name of the shared memory, and this name is same as the name that is passed here. So we have written the data onto the shared memory by name shm_1. So while reading also we need to open the same shared memory, and we are opening the shared memory in read-only mode, and if shm_open fails, it returns a -1, and we print the same and we return. So now we can get the size of the shared memory using fstat, and by passing the file descriptor to fstat we get the length of the shared memory, and finally we map the shared memory that is obtained from shm_open onto mmap. So by mapping onto the process virtual memory we get the map to the shared memory. So we have to pass null as a first parameter, followed by the size of the shared memory, and the protection to the memory is read, and this we have to specify as map_shared because we are using the shared memory, and fd is nothing but the file descriptor obtained from shm_open and the offset of 0. And if mmap failed, then we print the same and we return, and if mmap is successful we get the virtual memory of the process. And now any operation on this address we are actually performing the read and write of the shared memory. So now what we have done is we have opened the shared memory. We have opened the shared memory in process 2, and then we have mapped the shared memory onto the process virtual memory, and now we have got the handle of this shared memory as a mapped onto the virtual memory, and now any read write operation performed on this memory is in fact getting the data from the shared memory. So finally we print, by printing we do a read operation on the ADDR, that is nothing but the virtual memory address of the process. So now let's compile this program to understand. So we have compiled the program. So in order to compile the program of shared memory, we have to include -LRT. We have to specify -LRT, and shm_read is the object file of this program. So now we have shm_read and shm_write as the object files of read and write. So now let's first write some data using shm_write, and here let's specify the data. So now we have written the data. The data is nothing but hello_process2 onto the shared memory. Now let's run the shm_read program. Once we execute the shm_read, we are reading the data from the shared memory. So now we can see that the data that is written from the shm_write program, the same data is being read using shm_read. So using the concept of shared memory, the data is written from one process and read from the other process. So this is an example of shared memory, and shared memory is the fastest method of IPC.